Okay, so here we want to find a Maclaurin series for f of x equals cosine of x. So we're going to start off by writing out the entire series. So we have f of x is equal to the sum from n goes from 0 to infinity of f nth derivative 0 n factorial x to the n. And we know that this should be f of 0 plus f prime of 0 x over 1 factorial plus f double prime of 0 over 2 factorial x squared, and then we continue on. So the first thing that we want to do is just start off with f of x. F of x is just equal to cosine of x. So then when I take the derivative of cosine, you're going to know you're going to get negative sine of x. Take the second derivative of negative sine of x. It's going to give me negative cosine of x. Then I take the triple derivative. I'm going to get positive sine of x. So notice that I come back. Fourth derivative, cosine of x. And that's just stopped there. Okay. Now you want to do as many as you want, just so that you can try to figure out some of the patterns. So when you figure out the patterns, if after the third one you can figure out the pattern, then it's fine. But sometimes you might want to do a couple of them. So let's plug in 0 because we are looking for a Maclaurin series. A Maclaurin series is at a equals 0. Okay, so when I plug in cosine of 0, that's just going to give me 1. I'm going to plug in 0 into the first derivative. That's going to give me 0. Plug in 0 into the second derivative. I'm going to get negative 1. Plug in 0 into the third derivative. I'm going to get 0. Plug in that into the second derivative, into the fourth derivative, I'm going to get 1. So notice that you start repeating. So it goes 1, 0, negative 1, 0, 1, which kind of makes sense because that's just how the sine and the cosine curve look like. Okay. So let's go ahead and I can even do a little bit more if you really want me to. 0, and then at 6, when I plug in 0, it's going to be back at negative 1, so on. So let's go ahead and figure out what cosine of x should be. So cosine of x is going to be equal to all of this stuff, right? So let's go ahead and plug this thing in, okay? So f of 0 starts off with 1 plus f prime of 0, that just gives me 0 over 1 factorial x, plus now we're going to do f prime 0, f double prime of 0, that's going to give me negative 1 over 2 factorial x squared, plus now the next one's going to be 0 over 3 factorial x cubed. Then the next one is going to be the fourth power. So we're going to have 1 over 4 factorial x to the fourth. Then we're going to have the fifth power, 0 over 5 factorial x to the fifth. And then to the sixth power, negative 1 over 6 factorial x to the sixth, and so on and so forth. Okay, now I did more terms so that you guys can see where the pattern is going to be. So notice that all of these numbers, especially the odd ones, are all going to go away. So I'm left with 1. Then we have plus a negative 1 over 2 factorial x squared. Then plus a positive 1 over 4 factorial x to the fourth. Plus a negative 1 over 6 factorial x to the sixth. Okay. So can we try to come up with a general form of this? So n equals 0 to infinity. Okay. Well, the first thing that I notice is that there's an alternating sequence. Okay. Alternating series because it goes positive, negative, positive, negative. So I know that there should be a negative 1 at the end. Okay. Now notice that here, all of these guys are going up by 2's. Okay. So every single time I'm multiplying everything by 2. Okay. So this is going to be x 2 to the n. Okay. And then on the bottom, same thing. It's being multiplied by 2. Okay, so it's going to be 2n factorial. Okay, and this is going to be my final answer. Okay, so notice here, this one was a little bit harder, but finding the closed form can be a little bit difficult, and sometimes there's no closed form. So it is a little bit tough sometimes. But I will tell you first a couple of the main closed forms that you should kind of be familiar with. E to the x is equal to the sum from n equals 0 to infinity, x to the n over n factorial. Okay, these are centered at 0. Same thing with this one, cosine of x equals the sum from n goes from 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. Okay, this can kind of think about the evens. Then you also have sine of x. The close Maclaurin series of this is going to be negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, these guys usually, especially if you're going to take differential equations, you should feel very comfortable looking at these. Now, sometimes they might give you a table for them if you forget them, but just being able to see that series goes with this particular function is basically what it is. Now, one way that that you can use these types of series, and I'll just do a quick example about this just to finish up this chapter, is that if you wanted to find the integral of like sine x over x dx, let's say you wanted to find this integral. Well, this integral, you can't do it by hand. You cannot do it. I couldn't possibly tell you what the closed form of this is. Well, one thing that you can do is that, well, if I know what the series expansion of sine is, I can just literally plug this guy in here, okay, and try to figure it out. So the way that I'm going to try to do this is, well, I'm going to go ahead and move the 1 over x over times sine of x dx. I'm going to try to get the sine of x and plug in the series. 1 over x, then summation from n goes from 0 to infinity. I'm going to plug that thing in. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial dx. Okay? And now notice here, you have an x to the first power over here. That's going to get rid of one of those. So you're going to have the integral from the sum from n goes from 0 to infinity, negative 1 to the n, x to the 2n divided by 2n plus 1 factorial. That's just basically crossing out this one and crossing out the 1. Okay, now notice that because I changed it to a series, this is easier to integrate. This was hard to integrate. Now this is easier because all I got to do is just worry about this polynomial. So if I take out the summation, can take out the negative 1 to the n, I can take out the 2n plus 1 factorial. All I have to integrate is this x to the 2n dx. And this is really easy to do. That's just a sum from n goes to 0 to infinity, negative 1 to the n, over 2n plus 1 factorial. This thing is just going to be x to the 2n plus 1 divided by 2n plus 1 plus c. So now you have the sum from n goes from 0 to infinity, negative 1 to the n. I have this x to the 2n plus 1 on top. And then I have this 2n plus 1 factorial, and then I have this other extra 2n plus 1 plus c. Now, plus c you can figure out by plugging in a value of x. Now, this is really nice because even though I didn't have the limits of integration, if I had a 0 and a 1, then this is going to be really easy because all I got to have to plug in is just 0 and 1. Or I can just go ahead and expand this thing out. So I can expand this whole thing out, plug in the 0 and the 1, and then you'll be able to figure out what exactly this sum is going to be. Okay, so this is actually one of the greatest powers about series, that you can have something that looks really, really complicated and convert it into something that you can try to work with or program. Okay, so that's it for this chapter.